Alright, so I'm now going to talk about Laplace smoothing for the naive Bayes classifier, and this will get at the robustness of using ML estimation during training and how that affects prediction. And basically what we'll see is that using ML estimation can actually be a very bad idea. Alright? And so before getting into the details for that, I'm first going to talk about this probability. This thing we actually saw when I talked about prediction, because when we were computing the probability of a new email being spam, given these features, a little y1 up to yj, we used Bayes' rule, and in the denominator was this exact probability. And this probability can be interpreted as, what is the probability of observing these features we've extracted under the model that we have learned. Okay, so this theta we learned during training, and this theta consists of S, the PJs, and the QJs. And really these should have hats on them because they're values that we learned during training, but I don't want the notation to get cluttered, so I'm leaving off the hats. Alright, and from what we've talked about before for prediction, we can break it up into a spam case and a ham case. Alright. So getting into what the problem is with using ML. So let's say we use ML, maximum likelihood estimation, during training, as we were doing earlier, and specifically word 1 never appeared in any of our training data. Okay, so that means that we estimated P1, and again, this really should have a hat on it, but anyways, we estimate P1 to be equal to Q1 equal to 0 because word 1 never occurred. Well, what happens if we see when we're doing prediction, so for a new email, well, word 1 appears, meaning that y1 is equal to 1. Well, if you look at what happens to this probability, which is also called the evidence, basically, we're going to have, for the j equals 1 case, we're going to have 0 to the power of y1, which is 1. So this red thing is just going to be 0. And likewise, the blue thing is also going to be 0. So the probability of seeing an email where the first word appears under the model we've learned is 0. And in fact, we can't even choose between spam and ham in the sense that, if you remember, we use an odds ratio of this red guy divided by this blue guy. Well, they're both 0, so we've run into a problem. And you can imagine that there might be words in the dictionary that we just didn't see in our training data. So you don't want that to screw up your predictions. So, well, how do we fix the problem? Well, one way to fix this problem, which is Laplace smoothing, gets back to an idea we saw when I talked about estimating the bias of a coin if we put a prior on the probability of heads for that coin. And the result of the calculation was it was the same as introducing pseudo counts, which are basically fake observations that never happened. So how does that work for the naive Bayes classifier? Well, here are the ML estimates for the parameters for the naive Bayes model. If we introduce pseudo counts, here's one way to introduce pseudo counts, is the following. Alright, so what does this mean? Well, it means that we pretend that we observe one more email that was spam, and also one more email that was ham. So that's why here we have a +1, and then there's +2 in the bottom. And similarly for PJ hat, the probability of word j appearing in ham email, we're going to pretend that we saw one more occurrence of word j in ham emails, as well as one more no occurrence of the word j in ham emails, which is why it's +2 in the bottom. Similarly for the QJs, alright? So by introducing these pseudo counts, this guarantees that none of these parameters are estimated as 0, or 1 for that matter. So, in fact, you don't have to introduce a pseudo count of 1. You can introduce L pseudo counts for each of the possible outcomes, in which case, basically, you just get L instead. Alright? L and 2L. So, this is one way to fix the problem. It's called Laplace smoothing, also called additive smoothing.